Everyone, I am Rohit, and today I will be presenting our work enhancing novel object detection via cooperative foundational models. This work has been accepted to WACV 2025. Okay, despite the remarkable progress in AI, current models often fail to generalize beyond their training data distribution. Recent models are based on transformer, and they lack inductive biases which are present in CNNs. Uh, However, transformers have shown impressive scaling properties, which makes them centralized to only few major top companies which can afford to spend compute on increasing the scale. So, we will be addressing the fundamental challenge of generalization in a more accessible, cost-effective, and environmentally friendly manner. So, uh, it has object detection has wide range of applications, but current methods operate only under the closed set setting. They can't detect novel objects, and in an open set setting, we are also expected to detect novel objects like lamp, cushion, scarf, etc. So we tackle the open sets detection paradigm. So our contribution is that we leverage the strength of pre-trained foundational models like CLIP and SAM to transform closed set to into proficient open set detectors. Our modular design enables integration with existing state-of-the-art open set models like grounding Dino to enhance both known and novel class AP, and we obtain state-of-the-art results in open set, unknown, and open vocabulary benchmark. So to give a quick background, mask CNN, we use mask CNN, which is as shown in the below figure. The model comprises of a feature backbone, a region proposal network, and an ROI head. We also use Jitter, which is an transformer-based model for object detection, which treats the training objective as a direct set prediction task. The transformer decoder uses a fixed set of learned positional embedding called as object queries to decode object predictions in an image. The capacity of data to detect objects is determined by the number of object queries utilized during training. So this is denoted as n query. Foundational models are large-scale models which are pre-trained on massive datasets which can generalize to new data through prompt engineering, new data distribution. Ah, CLIP is one such vision language model which is trained on 400 million image text pair. CLIP is trained in this manner that we first create this text templates, a photo of an object where object is replaced by all the classes in your dataset. You pass it to text encoder and create n such text embeddings. And then you get an image for which you want to determine the class. You pass it to an image encoder, you get the image embedding. And then you do the cosine similarity matching between this image embedding and this text embedding, and you assign the class to this image for whatever text embedding maximizes the cosine similarity. In this case, this would be T3, which is dog. So we also use SAM, which is segment anything model. So it takes an input image and a set of prompts, which can be either mask, bounding boxes, or points. So it takes these and produces the refined segmentation masks. We also use grounding Dino, which is based on data. It incorporates Swing Transformer as its backbone. So for grounding Dino, it takes in a given image X and a text input of class names C, and it predicts the fixed number, which is equal to its number of queries, that is 900, of bounding boxes. And it also gives you the confidence score and the class labels. It involves large-scale training. Unlike this, our method combines existing pre-trained foundational models to exploit their complementary strengths to achieve superior performance. So related work is GNCD, which has mainly focused on semi-supervised and contrastive learning techniques. They also only focus on classification and they do not do localization. So these are some of the methods. Unknown object is another method which involves identifying and localizing known objects while only localizing novel objects without doing any classification. VOS and unsniffer are two such methods in this field. So the most similar method to our work is open vocabulary detection, and the goal of OVD is to recognize objects the system has been trained to identify, which is the base category, and objects it has not seen during training, which is novel category. So we consider VILD, OVData, object-centric OVD, which rely on knowledge distillation from pre-trained VLMs. Yeah. So though similar in name, OVD differs from our task of novel object detection as OVD uses additional weak supervision with a large vocabulary of classes, allowing for class overlap between COV and novel classes in OVD. However, we do not perform any such extra training, which is performed by OVD, and we also adhere to a strict zero-shot approach with no overlap. Thus, ours present greater challenge. RNCDL is another method which performs NOD, but it follows a two-phase training. The thing is, RNCDL shows very poor performance, and which does not make it practical for real world, and also it requires another separate validation set to assign semantic labels to the classes. So our problem statement is that we consider xi, comma yi, where yi comes from the space y train, and where the class label cj belongs to c node. So this is during training, d-train. However, during testing or during inference, we assume that the labels yi come from the space y test, and where y test is a superset of y train. Or the class labels during testing, cj, can belong to an extended set c, which is superset of c node. So our approach shows how to convert existing closed set detector to an open set detector, utilizing complementary strengths of pre-trained foundational models such as CLIP and SAM. Our mechanism leverages Clip's understanding of unseen classes with mask RCN and ability to localize background objects to find novel classes. Then we refine these boxes using SAM. So to show you an example, this is what closed set detector mask RCN has on known and novel AP. As you can see, novel AP is 0. If you combine this with our method, then novel AP will increase and also known AP increases a bit. If you consider an existing open set model like grounding dyno, which is a state-of-the-art model, and combine it with our method, then you can see further improvements across both known and novel AP. So this is our method where we use pre-trained models in initialization, unknown object labeling, and refinement stage. The first stage, which is initialization, involves initializing bounding boxes using off-the-shelf detectors such as mask RCN and grounding dyno. So here we use both mask RCN and grounding dyno and get the initial set of boxes. The output of these detectors based on conventional two-stage RPN are combined with complementary data architecture to compensate for weakness of each component. So mask RCN cannot integrate text easily, whereas grounding dyno is limited by the number of predictions which is fixed by num query. So we are able to complement the weakness of both by combining both of these predictions. So we just combine them. Before combining, we pass the background boxes from mask RCN to clip to get the class labels. So this is in the unknown object labeling. So for this, we use synonym averaged embedding generator. So here the text embedding corresponding to each class C. So here aerosol can is one such class. So basically aerosol can is one such class and spray can is a synonym of aerosol can, right? So we consider all the synonyms as well as all the class names, and then we take an average embedding over average across the synonyms and average across the class names. So basically, what we are doing is we get the set of prompted text for the synonym S. Here, we have multiple templates. There is a dash in the scene, a photo of a dash in the scene, a painting of a dash, where these are different templates. So, where T belongs to the templates. So these prompted text are then tokenized using clip to obtain their embedding. This is phi T sim. So here, n is the cardinality of this set PS, where this is the number of templates. So, and then what we do is we normalize this and average to obtain the representative text feature for a particular synonym S. And then we take an average over all such synonyms for a class to get the text embedding of the class. So, and then to get the final text feature matrix, we just concatenate all the text embeddings corresponding to each class to get this final dimension of D cross cardinality of C. And we just take cosine similarity between these text embeddings and image embeddings to compute the class prediction for the background boxes. So our final stage involves refinement, where we concatenate the boxes obtained from mask CNN and grounding dyno. This combined box, however, is inherently noisy. So we have to refine them. So we pass it to the SAM model as prompts, and we also pass the raw input image X to the SAM model. So this SAM model will then give us its own score predictions and output a refined segmentation mask for each prompted bounding box. So from this improved mask, we extract our refined bounding box BJ. And using the SAM scores, we use our SRM module to further filter out the low quality boxes. So how SRM module works is we get the combined scores SJC from the combined boxes, and we also get SJSAM from the SAM model. So once we have both of them, we do a normalization step by using min-max scaler, and then we just multiply element-wise these two quantities to get the final score. So this just filters high quality object predictions, as we only select those boxes which score high in both by the SAM as well as by the combined model. So we use Coco and Elvis as our data sets. Our principal evaluation is on Elvis validation set. Our known and novel split follows RNCDL. So for our results, we are able to show that our method outperforms even all the existing methods and even outperforms grounding dyno. So as you can see, even if we do not use grounding dyno, we are getting better all AP here. However, if you use grounding dyno, we can we can augment grounding dyno's capability using our method to further improve its performance. We also showed using a different VLM backbone, which is SIGLib, to show even improved performance gains. Similarly, we show state-of-the-art results on COCO open vocabulary detection setting, where our method achieves the highest novel AP50. We also compare against unknown object detection, and we get the best recall percentage. Further, this is the ablation on the refinement module. As you can see that our refinement module contributes to plus 4.40 novel AP increase in OpenSet mask RCNN and plus 2.45 known AP and of each component in our method, and we can see that the best results are obtained by when we use all the components: Cyclip, SAM, grounding dyno, SRM, our SRM module, and synonym averaged embedding generator module. So these are some of the qualitative visualizations. Third is mostly able to produce accurate detections, which existing methods like even grounding dyno fails. As you can see, it's giving it as table tennis, whereas our method gives it as dining table. Similarly, you can see other such qualitative visualizations on the project website. So to conclude, we introduced a novel cooperative mechanism that leverages complementary strengths of existing foundational models to tackle NOD. And we achieve state-of-the-art results in NOD, unknown setting, and OED setting. So our method transforms existing closed set detector into open set detector in training-free manner. And it can also combine with existing open set detectors to further improve its performance. That's it. Code is available on this, and thank you.